In this follow-up series, we are going to be looking at vertical circular motion, and in part 1 of this series, we shall introduce the conservation of energy. So let's define our situation that is vertical circular motion. What we're basically having is an object that is rotating around a circle in a vertical plane. And it is defined in this situation that we are going to take this object as it moves upwards, gravity will cause it to slow down, and as it moves downwards, gravity will cause it to speed up. So you can model it as if there was a tension force acting through the point O onto the object, and you're basically spinning this object around with the tension of the string. Alright? So therefore, in vertical circular motion, the speed varies, which is different from horizontal circular motion. So knowing this, as you rise, your speed decreases. So therefore, at the highest point, your speed cannot decrease any further before it starts to increase again as you go down. Therefore, the speed is the least. And at the lowest point, your speed cannot increase any further. So therefore, your speed is the greatest. And in horizontal circular motion, we know that the resultant force acting on the object remains the same, but in vertical circular motion, the resultant forces acting on the objects will be different, and therefore there will be varying centripetal forces, and therefore their acceleration can be seen as two types. One as linear acceleration, and this is due to the speed varying with time. Remember, vertical circular motion, the speed varies. But for vertical and horizontal circular motion, they will both experience radial acceleration, and they will always be resulting due to the constant change in direction. Alright? The velocity of an object as it moves in vertical circular motion, just as in horizontal circular motion, will always be tangent to the path of the circle in which it moves. And the centripetal force will always act perpendicularly to the direction of the velocity. Same for horizontal circular motion. And since the resultant force acts in the perpendicular direction to the direction of motion, there will be no work done in the direction of the motion. So therefore, the principle of conservation of energy applies. So at any point on the circle, the total mechanical energy remains constant. In other words, the total kinetic energy and gravitational potential energy is constant. So if you're going to take two situations where point 1 and point 2 you're going to consider, then the kinetic energy and the gravitational potential energy of point 1 is equal to the kinetic energy and the gravitational potential energy of the object in point 2. Alright? So let's look at that in a context. So we know that GPE and KE is constant. So when we're looking at the bottom, in where the object has a speed of v1, the total mechanical energy is half mv1 squared. We're going to take the height, the position of the object when it has v1 velocity as 0 height. Okay? So therefore, the total mechanical energy is 0.5 mv1 squared. And at the middle position where the speed is v2, the total mechanical energy is its kinetic energy, which is half mv2 squared, add the gravitational potential energy. At that point, at that height above the fixed position, we are going to take as mgh. And therefore the total mechanical energy is 0.5 mv2 squared at mgh. So therefore, we come up with that ratio by combining the two equations. And when we look at, now what if the difference in the two positions is separated by an angle? Alright, so we do the same. We consider the bottom first, which is KE plus GPE is equal to half mv1 squared, exactly the same. But in the other position, we're going to have to do some careful trigonometry. So let's look at the other position first. So at the other position, the total mechanical energy is equal to its kinetic energy, which is half mv2 squared at mg at a height of x. So at that height in which the object is from a fixed point, we're going to call it x as it indicated in the diagram. And we're going to do some careful trigonometry, which we can find out that value of x is equal to h minus h cos theta, where h cos theta is that small segment, the small part that is of the h cos theta by your SOHCAHTOA rules. So therefore x is equal to h cos theta. We can then combine it into the equation to find the total mechanical energy at the other position, which is half mv2 squared plus mg by x, which is h minus h cos theta. And we combine the two ratios to give that ratio. And this is basically a formula that you can use every single position about the circle relative to the bottom negative. Alright. So let's look at some key. And to sum up this video, we're going to be showing you some few important tips. One of it is that the speed varies around the circle. Why? Because the centripetal force varies around the circle. But the centripetal force will always act perpendicular to the direction of the velocity, so therefore there will be no work done in the direction of the velocity. So therefore the conservation of energy applies, and you can solve every single question based on the conservation of total mechanical energy. So thank you for watching my videos, and I hope that you do come back to watch the previous circular motion videos, and those are very, very important. And the next video is basically going to be a part 2 on the forces acting on an object as it undergoes vertical circular motion.